Right, welcome back. How's everybody doing today? Let's see, I'm in the wrong chat. I'm going to open something up so I see you guys. So just tell me about what's going on. How's life? How's school? All that kind of stuff. Here we go. If we could find our one for today, physics. We are talking today about let's see, let me bring this down here. Convex and concave mirrors. Hopefully you guys, everybody took a spoon and checked out what we looked at, checked out what I showed you guys with the spoon. I think it's super cool. They can just do that with a spoon, and you can see that. You can flip it around and you'll have a convex mirror, and you can see how that looks on the other side. But I like it's how when you bring it really, really close to your eye, you can actually see your eye get really, really big. So hopefully you guys all try that out. I'm not seeing your comments right now, but let me just get this thing started and hopefully I will. All right. Why is this doing this? Oh, here we go. Here we go. So I see Jeremiah, Adam. Hi. And let me see, anybody else here today? We got, oh no, it's just you two. I only see two. So hopefully everybody else is going to join us soon. And yeah, hopefully, let's see. Just trying to open this up. Let's get to the top here. There we go. There we go. Okay. Why is this not actually, okay. Now we got it. All right. So we're going to go through 1 to 4 for the homework. And like I said, I find these can be a little bit strange and challenging at first. But after a while, you're going to get used to them. So like I said, please put a lot of effort into them at the beginning. Don't wait a week to try to figure this out, okay? Put a lot of effort into it at the beginning. Then after a while, these drawings will become second nature to you and they will not be difficult because you're going to use the same principles when we do the drawings for the lenses and all that. And so same kind of stuff for different types of mirrors, different types of lenses. Very, very important. So make sure you put the effort in and then it'll get easier and easier the more you do. Okay, so number 1, let's do this. We're going to find the image distance and magnification of the mirror in the same problem as the sample problem when the object, let me see, distances are 10 centimeters and 5 centimeters, and are the images real, virtual, all that kind of stuff. Okay. So we didn't really, I forgot, or we kind of ran out of time, so we didn't get a chance to really talk about the magnification, but we're going to get to that today, and then we're going to also get to, let me actually see if I can put this in a different way, and then we're going to go through all these different mirror drawings and that. So if this will flip around, no, it doesn't want to flip. Okay. Never mind. Never mind. We're just going to do it this way. All right. So number 1. We're going to solve number 1. We have, it tells us the image distance we want to figure out, right? And the image distance, that's going to be Q. And it says the object distance are 10 centimeters. So your P is going to be 10 centimeters and then 5 centimeters. So we have the same kind of situation. These are this is literally 2 different questions. And we have to go back to the sample problem to figure out, okay, what else do we know about this particular mirror? And so it says back in the sample problem, we had we had an F of, I can see here. It was 10 centimeters, is that right? In the sample problem, F is 10 centimeters. F equals 10 centimeters. I'm pretty sure that's right. Let me just go back just to check it out. Yes, 10 centimeters. And then our sample problem was an object distance of 30. And here we have 10 and 15. So basically what we're doing is we have exactly the same exactly the same mirror as before, except now we're taking that object and moving it closer. And I'm always going to draw little trees because I like to draw little trees, and you can draw whatever you want. But I find trees to be nice because it's really, really clear where's the top and where's the bottom, and they're easy to draw, as opposed to some objects are not so easy to draw, whereas a tree is super easy. So let's start off and do the math first, and do the equation first, and then do the drawing next. But you can do the drawing first if you want. Either way is fine, however you like to do it. So we have the equation in all of these, 1 over p plus 1 over q equals 1 over f, and not forgetting what everything is. Let me just label it just to make sure we are all remembering. P, that's going to be the object distance. Q, that's the image distance. And f, that's the focal length. And we remember that f equals 2r times the radius. So it's related to the size of the mirror itself, okay? So that's all kind of the relationships we mentioned before. Also, I kind of didn't have time last time, and so we didn't talk about the magnification. And so the magnification is related, well, it's exactly kind of what you would think about. It's how big the object gets, or how small the object gets. And so we have the magnification equations, and I'm going to go ahead and just do them right down here. So your magnification is going to be equal to the h of the image divided by the height of the object. Your book might write this a little bit differently, but I think this makes a little bit more sense. So the magnification is defined as the height of the image divided by the height of the object. And so if the image is bigger than the object, the magnification is going to be greater than 1. If the image and the object are the same size, the magnification is going to be 1. And if the image is smaller than the object, the magnification is going to be less than 1. So the magnification, we typically don't actually calculate the heights there. And so instead, we have this equation that I believe is derived in the book for you. It's negative q over p. At least for mirrors, it's negative q over p. So let's see. I think a little bit more light might help. All right. So question, isn't f equal to 1/2 r? Yeah. Good call. Is it q divided by p? Yeah, it's q divided by p. Actually, I'm sorry. You're absolutely right. I made a mistake here. So f is, sorry about that, 1/2 r. You're absolutely right. It's 1/2 r. It's closer to the focal length is closer to the mirror than the center. So f is 1/2 r, or sorry, r is 2f, or f is 1/2 r. Thank you very much. But magnification is the image height divided by the object height, which is equal to, or can be derived from, negative q over p. So this is kind of your derived equation for magnification, and this is your definition of magnification. All right? So with that, armed with that, let's go ahead and solve these equations here. And that is for two parts to this. You have p equals 10 and f equals 10. So when p equals 10 and f equals 10, that's going to give you the equation, and let's use a different color for this. That's going to give you the equation of 1 over 10 plus 1 over q equals 1 over 10. And we have a problem there, right? So what's going on here? If you have 1 over 10 plus 1 over q equals 1 over 10, you're going to end up with what? You're going to end up with 1 over q equals 0. And so in this case, your q is going to be undefined. So if q is undefined, or you could almost say that q is going to be approaching infinity, right? because as q approaches infinity, 1 over q is going to approach 0. Oops, this is off the page there. So as q approaches infinity, 1 over q is going to approach 0. So you can think of this as q is undefined or q is infinity. And so what does that mean in terms of an image? That means that there is no image. And you guys, or at least I don't know about everybody else, you guys may have seen this. If you look into a spoon and you bring the spoon closer and closer and closer to your eye, you will get to a point at which there's no image. You see nothing. And that is the point at which you are looking exactly, your eye is right exactly at the focal length or the focal point. And if you get your eye exactly at the focal point, then you're going to have no image, right? So, and think about this. So that was when p equals 10 and the focal length is 10. So anytime for a concave mirror, anytime your p equals f, your image distance and your focal length are the same. So in other words, your image or your object distance and your focal length, if your object is right at the focal point, you're not going to have any image. Okay? There'll be zero image at all. All right? And so we can actually do a drawing for this one, and let's go ahead and try that out. Let's try a drawing for this one. And what we're going to do is, here is our principal axis, and here is our mirror. And let's draw I should have made that blue. Now I have to make a green Christmas tree. Okay, here is the focal point, and here is the center. So this is 10, and we're going to put this tree right here. Okay? And so our drawing should be like this. There are 3 different ways that we can do this. I showed you guys 2 different ways that we could do this last time. Again, we kind of ran out of time. We can do this 3 different ways. I don't know if the book mentioned them all, but there's 3 different possible ways to draw them. To draw a mirror diagram. And that is this. You can draw parallel to, I'll just abbreviate this, principal axis. PA is principal axis. Then it's going to reflect through F. Number 2, and you don't need to do all 3 of these, you just need to do 2 of these. So we're going to draw through F, and then you are going to reflect parallel to the principal axis. Okay? And number 3, we can draw, through C, through the center, and then reflect back through C. All right, and I think last time we did numbers 1 and 3. You can do 1 and 2. You can do 1 and 3, 3 and 2. You can do, whatever kind of, combination of those. But you only need 2 different lines in order to actually see what's going on. All right, so let's go ahead and do the drawing for this one. A little bit strange when you're actually on the focal point, but let's see what happens. So if we draw in parallel to the principal axis, it'd be nice to have a clear straight edge. So it'd be a little bit clear. That's not even exactly parallel, but anyway, whatever. So when you draw in parallel, it's going to reflect back through F, through the focal point. Okay? And when you draw in a line that is through, let's see, you can draw this, let's say maybe through the center. That's kind of, yeah, let's just do that one. If you draw a line that's coming through the center and bounce it this way, it's going to bounce back through the center and come back out. So light coming through the center is going to come back out. And you notice what? You notice that these two reflected lines don't intersect. Yeah, they intersect here, but that's before, this is the incoming light, okay? After they reflect, what happens to this? The light keeps on coming and going like this. And these lines, these two lines are parallel and they never intersect. And that's basically what it means by your Q is undefined and you have no image. So that was been probably a kind of a tricky one to solve there. Okay, so all right, so is F equal to 2? So R is 2F or F is 1/2 R. So sorry about that, I made a mistake earlier. So, and you look on the mirrored drawing that we did before, which, yeah, I don't see it. So if you look at the mirror drawing that I did before, you'll notice that and you can look right here actually. So this is F and this is C. So your distance, so your R, this is your R distance and this is your F. So F is 1/2 R, okay? Or rather the numerical values of it. Yeah, so F, capital F is the focal point, lowercase f is the numerical value. Lowercase f is the focal length, and capital F is the focal point. Capital C is the center, and then lowercase r is the radius. And so radius is going to be 2f, or f is going to be 1/2 r. Okay, so those are correct now. So use r to determine c. Typically, yes. Sometimes, however, you'll be given c in the problem, and you'll use the c to determine, or you'll be given r in the problem, you'll use that to determine f. So it all depends on the specific problem. So we're only half done that problem. So let's go ahead and do the other half of that problem, and hopefully the other ones go a little bit faster. So here we go. We have same situation. Once again, for number one, the second part, we have f is 10 centimeters, but now we have p is 5 centimeters. And same equation, 1 over p plus 1 over q equals 1 over f. And, oh, and by the way, if we have something like this, the first part, you can't really calculate the magnification in that case, right? Because you have an undefined q, so there's no magnification. If there's no image at all, there's no magnification. So you just basically say, you know, no magnification or undefined or something like that, right? All right, so back over here. This one is defined. We are going to get actual numbers here. So if f is 10 and p is 5, we can go ahead and calculate q. So let's plug in the numbers. 1 over 5 centimeters. We're just going to leave everything in centimeters, and so I'm just going to forget about the units for right now. Plus 1 over q equals 1 over 10. And so 1 over 10 minus 1 over 5, you can do that in your head, is probably, so this is 2 over 10, so that's going to be negative 1 over 10 on this side, right? So you can do it in your calculator, but let me just say, so that's going to give us a 1 over q equals negative 1/10. And I'll do it in my calculator just to verify and show you guys that that's going to work, right? So you can do in your calculator 1 divided by 10, right, it's 0.1, and then subtract 1/5 from that, and you get negative 0.1. And so once you get negative 0.1, you get negative 1/10. All you need to do is flip it, right? And so it's going to be negative 10. So q is going to be negative 10. And so we take the inverse, right, negative 10. So q is negative 10. And so now we can go ahead and do some calculations with that. And the calculations are going to, first, we need to say, well, what's the magnification? We said the magnification for these is going to be negative q over r. No, I'm sorry, negative q over p. And our negative q is going to be negative, let's just write the whole thing out, negative 10 or positive 10. And p we said was 5. And they're both centimeters. This is centimeters, so this is centimeters. So our answer should be unitless. Magnification is always unitless, and magnification should be 2 for this. Okay? And so before we even draw this, we can get an idea of what is going on here. And first of all, we can say, okay, from the magnification, we can say that this thing is bigger. Specifically, is twice as big. So the image is twice as big as the object. Secondly, we can say, oh, this Q is negative. What does that mean? That means that the image is virtual. And it's going to be behind the mirror. It's going to be on the other side of the mirror. And secondly, because the magnification is positive, when the magnification is positive, this thing is going to be upright. And that's another thing that I don't think we mentioned last time. So a positive magnification is an upright image. A negative magnification is an inverted or upside down image. So this is going to be bigger, it's going to be upright, and the image is going to be virtual. It's going to be on the other side of the mirror. Okay? So let's see if our predictions or if these calculations are correct. We're going to go ahead and do the drawing. And the drawing is going to be like, let's see, like this. Here's our principal axis. And on the principal axis, we have, this is going to be 10. This is going to be 20. This is our C. This is our F. And we have a tree or an object that's right at 5 centimeters. So if this is 10 centimeters, then our object is going to be right there in between the focal point and the mirror. And so we're going to go ahead and do a couple drawings in. I like the whole center one, and we're going to do, let's do we can go parallel in, or we can go through the focal point in. Let's do it this way. All right. And it shouldn't matter exactly what you choose. And I think I'm going to actually run out of space here because this is going to get bigger. So focal point in, and then it's going to go parallel out. And what you're going to notice is that the lines don't always necessarily cross on the real side of the mirror. Sometimes they're going to cross on the other side of the mirror. And when they cross on the other side of the mirror, we're going to need to extend not the incoming light, but the outgoing light. Okay? So I'm not going to extend this beam of light over to the other side, over to the virtual side of the mirror, but I'm always going to extend the reflected light. So this is my incoming light, and then it's going to bounce off parallel. So in through the focal point and bounce out parallel. Okay? I could have done parallel in and bounce out through the focal point. That would work too, either way. But I'm also going to do through the center because I just like to go through the center. It's one of the easier ones. So it's going to go exactly, let me see if I can get the center exactly right here. It's going to go in here and then bounce straight back. But notice the lines are not going to cross on this side of the mirror, so I need to extend it over to the other side of the mirror. Why? Because our reflected line, so this is a reflected line and this is a reflected line, notice that they don't touch on this side of the mirror, right? These do not touch, or they don't intersect on this side of the mirror, so the image must be on the other side of the mirror. And this is one of the things that that is so tricky for drawing these things, that you need to recognize that when you extend these lines to the other side of the mirror, you're always extending the reflected line. So what did I do here? When I went in through the focal point and I bounced out parallel, I extended the reflected parallel back to the other side. All right? It doesn't make a big difference for the center because center is just in through the center, out through the center, like that. All right? And see where they cross. They cross on the other side of the mirror, right over here. And notice that this is indeed bigger, right? The top of the tree is way up here. It doesn't look like it's twice as big, but it's approximately twice as big right over here. And notice, so this is 5 centimeters, this is 10 centimeters, and yes, this indeed is 10 centimeters is about the same distance as this. So this is really, really corresponding to what we're seeing over here. This is a Q of negative 10. It's 10 centimeters behind the mirror, right? This is a magnification, a large magnification, so a magnification of about 2, so it's bigger, and it indeed is upright. So, some questions. Given that our eyes' lenses flip upside down, image, whatever we see, are we always looking at a virtual image? No, we're not always. So upside down doesn't mean virtual. Yes, our lenses flip the image. And you're going to find that some of what we talk about for mirrors is the same as lenses, and some of what we talk about for lenses is the opposite of mirrors. So we're going to find that we're going to talk about lenses later. And there's going to be a lot of stuff similar, but some of the stuff is going to be a little bit confusing because of that. But the upside down image that we have in your eye is a real image. And that's how we can actually see the real image, because that real image is touching a screen, and that screen is the back of our eye, is touching our optic nerves, and or the rods and cones in our eye, which go to the optic nerve. And so that's how we can actually see things. So it must actually be a real image, and it is. So we're not always looking at a virtual image, we're always looking at a real image, but you're right, it is upside down. How do you know when to draw the line through the center from the ground up or from the sky down through the center? Oh, so it's always going to go from the center to the top of the tree, okay? So the reason I'm going up to the tree is because the tree is on this side of the center. If the tree, however, were, let's suppose, now I need to get a different color here somehow. Let's suppose my tree was over here, Hannah, okay? If the tree was over here, then I would go up from the sky through the center, okay? So it's always, you're always connecting the center to the top of the tree or to the top of the object. That's what's going on there, okay? So when you're doing the number 2, the center in, center out, is always going to be from the center to the top of the object. And same thing with, let's say, going through the focal point or going parallel. When you go parallel in, it's always going parallel and then hitting the top of the tree, or going through the focal point, hitting the top of the tree. So you're always going to the top of the object, okay? All right. Now, let's see, what's next? Oh, we've done a whopping 1 problem. Let's go on. If we need to take some more time for this, we can. So I want to make sure that we're making some sense of this. Number 2. Let's be... Okay. Oh, and I love my book just reset everything. So we're going to go back to hitting all these things, plan, solve. I think we might even take a break. Yeah. Oh, shoot. Did I just hit reset? That was so... Yeah, I just love the way their book does this. Can't believe this. Practice. All right, there we go. Number 2. We have a concave shaving mirror. All right, shaving mirror. This is annoying. I'll turn the light back on in a minute. Concave shaving mirror. It's got a focal length of 33 centimeters. All right, nice. So F is 33 centimeters. Calculate the image position. So we want to know, once again, we're calculating that Q of a cologne bottle. I'm not going to draw that cologne bottle. I'm going to draw a tree. Jeremiah can draw a nice, beautiful cologne bottle. I'm sure he has, but I'm just going to draw a tree. All right, placed in front of the mirror at a distance of 93. So we have a P is 93 centimeters away. Calculate the magnification of the image. Is the image real or virtual? Is the image inverted or upright? Draw a ray diagram to show where the image forms and how it is with how large it is with respect to the object. All right, let's do that. Nice. So back over here. Let's do the math first and then do the ray drawing here in a second. So we have our equation 1 over f. That's going to be 1 over, we'll do the 1 over p. So 1 over 93 plus 1 over q equals 1 over f, or 1 over 33. So that means 1 over q equals 1 over 33 minus 1 over 93. And let's go ahead and solve for q in our calculators. All right, let's do this. 1 over 33 minus 1 over 93. And then I'm just going to take the inverse of that. And then boom, 51.15. 51.15. Answer should be in centimeters. We should probably just round that off to two significant figures and just say it's 51, but I'm just going to leave it. And then we want to calculate, let's calculate the magnification. Magnification is going to be negative q over p, which is going to be a negative 51.15 centimeters over p, which is, we said p was 93. So let's do that. Let's just go divide by 93 and then make that a negative. That's going to be a negative 0.55, negative 0.55, and magnification has no units. So what we can say, we can already describe this thing, right? So what does this mean? This means that Q is positive. If Q is positive, this is a real image. A real image simply means that we can project it onto a screen and observe it as onto a screen, right? And because this is negative, the magnification is negative, not Q. When magnification is negative, it's upside down. When Q is negative, it's virtual. So magnification is negative, which means this is upside down. And it's also smaller, right? It's about half the size, but not quite half the size. So this is going to be, right, smaller. And so let's see if that's exactly what we get when we do this drawing. And so drawings, super important. Probably you guys are going to be struggling more with the drawings at first than you are with the actual calculations. Excuse me. So let's do the drawing. Here we go. All right. And we have, let's see. So this is, F is going to be right here. This is going to be 33. And then this is going to be 66. And then 99 is right here, and the object is at 93. So we're going to put it like right there. Where's my green? We want green. I like Christmas trees. Boom, right there. That looks like right about 93. Now, this is all really approximate. So don't expect your drawings to always be perfect, but your image should be in the right place and smaller or bigger accordingly, okay? If it's not perfect, you know it's not perfect. It is what it is, but you try to make it as good as possible. So once you got that, we get everything we need to make a nice drawing here. What I'm going to do first is I'm going to go, let's go parallel in, which is kind of standard. And because mine's not clear, I'm going to put my ruler upside down like this so we can get a nice straight line in. There we go. So parallel in, right? Always we're going parallel in. We have to go right on the top of the object, so the top of my tree, and then it's going to reflect out. And when it goes parallel in, it's going to reflect out through the focal point, which is right about there. I think that's good. Okay? And then I can go, let's do center. Center is just like the easiest one to do. Okay? So center in, center out, just like that. Of course, I don't have to. I could go, what I could do is focal point in and then parallel out, which is perfectly fine. You can do either one, but I like to do center because it's just one of the easier ones to do. And we're coming up from outer space here, coming up from space because the object, the tree, is to the left of the center. So let's go right about there. That looks about right. going in and then out is the same. So in and out. Now notice these two lines, the reflected lines are the ones that matter, right? Not the ones coming in. The reflected lines, so this is a reflected line, and then this is a reflected line. Where the reflected lines cross, that's where your image is going to be. And so I'm going to draw a tree right there. This is where the reflected lines cross is the top of your image. So because that's the top of our image, I'm going to go from the parallel axis down. The bottom of the object is always going to be along the parallel axis, okay? So it's going to be from there down, and this is my tree. And we notice, look, my tree is upside down, and it's smaller, and it's real. It's real because it's on this side of the mirror. It's upside down because the reflected lines crossed on this side of the mirror, and it's smaller because they reflected, well, this is just where they happened to reflect, and the thing got smaller, okay? All right, so it's 3:17, which is, man, it's been just taking me forever. You know what I want to do? I'm going to do this. If you guys made any mistakes on your homework, correct them, fix them, and fix the other problems. I'm just going to say no homework, okay? We're going to say the homework that I gave you guys is going to be due on Tuesday. And I want you to take the time to really make some sense of this and correct anything that you did so that you can come to class on Monday. We're going to go through numbers 3 and 4 on Monday so that you guys can get really good at these drawings, and the calculations I think you'll be fine on, and make some sense. Make sure you know what does it mean to be real or virtual, upside down or inverted. So you can say, so upside down or right side up, and smaller or bigger, all that kind of stuff. So make sure that you guys can make some sense of this stuff, and then we'll come back on Monday. So the homework that I signed, I'm going to turn that in and change that and make that to be due on Tuesday. And then we'll talk about your convex mirrors on Monday. Okay? But get this stuff right. See you guys. Have a great rest of your day and have a great and wonderful weekend. One last thing, just a last little plug for Chess Club. For those of you who like to take as much time as you want, we are having a 3-day tournament, 3 days, meaning 3 days per turn. So this tournament could literally last a month if people, if we have very long games. But of course you could have a game that lasted a lot less if people are logged in at the same time. But I probably won't do that because I don't like sitting around for 10 minutes waiting for somebody to move. So I like either super fast chess, or I'll like look at the board and then just move real fast and then close the board, because that's me. But anyway, if you're interested in chess, I know that that Adam is in it. I don't know if Hannah, I think Hannah signed up too, so Hannah and Adam are in there, so ask them. I also have the link, and guys, you should join. It'll be a lot of fun. All right, anyway, have a great weekend. See you guys. And once again, the homework that I signed is not going to be due till Tuesday. All right.